Good morning, everyone. My name is Chao, coming from Department of Electrical Engineering, National Jiao-Tong University, Taiwan. It's a very good opportunity over here to introduce to you the research work we have done on the energy harvester. Our laboratory have been establishing a new energy harvester device, which is called hula hoop motion device. However, that device is not a focus of the presentation I'm going to give. The focus of the presentation today is on the front-end convergent energy harvester power circuits. So this power circuit is actually shown over here. It's actually a charge pump, AC to DC charge pump. We have been presented this charge pump circuit topology last year. So last year is the first prototype of the circuit design, and during the 1 year after that, we have been trying to optimize the circuit topology. So the primary focus of the presentation I have today is on the progress. Actually, we have changed a lot last year circuit topology. Here's the outline of my speech today. I give you the highlight and basic concept of the circuit I'm going to introduce to you. And then going to show you the process of optimization on these circuits. And then the whole overview, the picture of the energy harvest circuits. And then introduce to you some additional revision on the circuit topology we have been introduced last year. And finally, we have fabricated the chip, and there is some experiment data have been collected and it will be presented today. Finally, the conclusion and the future work. Okay. Here's probably give you an idea of what's the energy harvester. I think most of you over here in this room know what's the concept of an energy harvester. Okay. Energy harvester is essentially trying to collect the energy available in our environment, such like we have a solar power, temperature gradient, acoustic noise, or vibration. This study particularly focuses on how to collect the vibration energy in an environment or in a vibration machine, dynamic machine, into the electrical power. So the method, the approach we have been adopted in the past several years is trying to use electromagnetic power conversion. In other way to see this kind of device, this is later. So having a generator which is designed perfectly to convert the vibration energy to electrical power. That electrical power will be actually the AC power. That AC power, suppose for many of my is actually accept only the DC power. So there is a requirement that for many, especially consumer product application, okay, we need to convert the AC power over here from the generator to a very stable DC power. Okay. So the box over here is doing the power conversion from the AC power to a DC power. Whenever you're trying to do the power conversion from the AC to DC, the power consumption is going to be happen inside this box. So what we have proposed is at the very front, there is a AC-DC charge pump, which is a 100% brand new topology. These circuits, we have just have about 6 months ago, we got a US patent for this topology. And then after the charge pump, there is a power management unit. This power management unit is trying to manage the DC output voltage in order to have a very good efficient after this power management that we have a LDO in order to either provide power to a device, consumer device, or provide power to the battery for temporary energy storage. Okay. So at the very front, we have this charge pump topology, which essentially consists of two different parts. The upper part and the lower part, they are mirrors to each other. Okay. The principle behind is actually we try to operate this AC to DC charge pump by alternating two different states. Okay. State 1 and state 2. In the state 1, okay, the upper part, all the capacitance in the upper part is charged in the topology of a parallel capacitor. And at the same time, the other part is discharging. But when you discharge, all the capacitor over here is actually in the series connection. Okay, that's what happened in the state 1. What happened in the state 2 will be the opposite. Okay, if any of you over here in the room are aware of the operation of charge pump, you may know that for ordinary charge pump, you need to have a switch and you need to have an external clock. Okay, one of the beauty of this circuit topology is there's no switch at all, and switching between state 1 and state 2 is automatically done by the incoming AC voltage signal. So if you are the charge pump designer, you know for the RF circuits, there is a Dixon charge pump or a lot of variation over that. So whatever kind of a topology you adopt, you need to use a switch or external clock. But for our circuits, there is a not requirement at all to use the external clock. So here is the detail of operation principle. So in a state 1, we're going to charge this capacitor and discharge this capacitor. That's the way of we operate these circuits. And at state 2, when the incoming AC voltage signal is at second period, so the operation of this circuit is actually in the other way. Okay, so these capacitors will be charged in parallel, and then these capacitors will be discharged in a series pattern. Okay, so that's our very special design of the charge pump circuits. Okay, in those charge pump circuits, there is diodes. Okay, whenever you use diode, there is going to be voltage drop across the diode. Then those voltage drop will cause you some power consumption. So we particularly design over here the new type of the diode, which is not essentially just one diode. There will be a circuit design over here. Okay, there is one particular mode switch over here. The on and the off will particularly control by comparison of the VD over here, the input voltage and the output voltage. So it will automatically, again, there is no switch, automatically determine it's on or off, essentially perform the same job of a diode. This topology is not 100% new. There is already some dropless diode circuit topology that is constituted by a couple of MOS switch has been presented in the past 10 years. Okay, but there is some slight variation, actually, which is different from all the different dropless diode circuit you have been available in the literature. So the other thing is when we try to design this circuit, so the first step is to determine the topology. The second step is try to optimize. Okay, the optimization for this circuit is for the purpose to have a best power efficiency. Okay, in order to do that, okay, all the capacitance we have been talking about in the circuit topology has to be optimal size. In other words, we need to find the best value for all the 6 different capacitance in order to have the best power output. Okay, one of the reasons is that there is a resistance everywhere. Okay, for example, across any mode switch between D and S, there is a equivalent R on resistance. So for the purpose of the optimization, we need to find the equivalent circuits first. Okay, you will come from the first. We need to have the equivalent model of a generator. Do a little bit about simplification, and it's simplified to the circuit over here. On the other hand, we consider all the capacitance in a charge pump, okay, and simplify all these components to the combination of resistance and the capacitance. And finally, combine the front part and the rear part to this very simple circuit, which is supposed to be very much equivalent to original charge pump circuits. So you can see this circuit is very simple. Okay, if we want to have the best power conversion efficiency, which means hopefully all the energy coming from the generator will finally 100% goes to these capacitors. But however, that's not going to happen. Okay, must be some power to be consumed by this equivalent resistance. Okay, the basic idea of for the best power conversion is very simple. It's in the undergraduate study textbook. Okay, it's called impedance matching. So, but now we have the output impedance, and also along the way for the current, there's some other resistance. Probably we can try to model to have a certain level of precision. So later on, we're just trying to perform some kind of a generalized impedance matching to figure out what's the best capacitance we should have. Okay. So here's the detailed step we have conducted to perform the optimization. For step 1, okay, it's actually all the capacitance is in the charging state. So finally, based on, I'm not going to go to the details of all the mathematics manipulation. In the end, based on generalized methodology of impedance matching, finally you can find the optimal capacitance. Okay. So once you have decided the optimal value of a capacitance, okay, we have designed a chip and the fabrication and conducted the experiment, and finally try to compare the experimental result with our theoretical predicted, our theoretical simulation with the optimal capacitance we have been found out. So here's 3 different figure for different specs. Okay, here we have the incoming AC voltage, which is in the different frequency, 20 hertz and 40 hertz. On the other hand, we assume there are 2 different types of a generator. Okay, they have 2 different internal resistance, 5 kilo and 2.5 kilo. Okay. In each figure over here, there are 2 different curves of the data. One is the simulation, the other one is coming from the fabricated chip. Essentially, it's experiment data. So you can see there are, although there is a difference, okay, because the difference probably coming from the non-ideal factor have been involved in the real chip. But however, if you particularly pay attention to the maxima, okay, in all of these 3 figures, maxima of the 2 curves, for example, for this one, is actually corresponding to essentially a very narrow neighborhood, the area of the frequency, which means that the optimization technique we have already adopted in the previous two slides, which is actually effective. So that optimization about step one, in which the three capacitors is in charge. Okay. And step two is discharge. So essentially have found very good correlation between the experiment and the chip. Okay. So other than design, okay, we also try to design so-called over here the state select charge pump, which is in the topology of this circuit and this circuit to be combined. Then with these kinds of topologies, then we can control the output voltage over here to optima when either it's incoming AC power level or high level. Then we be ordered to use different stage, different number of capacitors. Then we can, okay, then we can have a very good power conversion. So here's the picture of the layout and the chip. Okay, here's the conclusion. Okay, the proposed have been successful rectified the AC power to DC power, and the arrow, the maxima, the optimal frequency is actually within very small, 0.6%. And then it's a very good topology and way to find out what's the optimal capacitance to have this kind of AC to DC charge pump conversion circuit.